Hello everyone, I'm Xudong from University of Illinois, and today I'm going to talk about how to build provably correct production-grade cluster managers such as Kubernetes using Anvil. This is joint work between University of Illinois, University of Wisconsin, VMware Research, and Feldera. Cluster managers such as Kubernetes, Borg, and Twan are among the most critical system software running in modern data centers. They manage the clouds and all the applications running on the clouds. In particular, Kubernetes is an open source, widely used cluster manager. And similar to other cluster managers, Kubernetes is architected as a fleet of controllers. Each controller here runs as a microservice. And this controller implements all of Kubernetes cluster management logic. Different controllers here manage different applications, services, and resources in the cluster. So controller correctness is very critical, but also very challenging to achieve. This is because controllers run in highly asynchronous and concurrent environments, and they need to handle unexpected failures such as crash and ending points. So we started with testing controllers for the past few years ago. We developed testing tools such as SIL, a fault injection testing tool, and Acto, a fuzzing-based testing tool. And through testing, we have discovered over 100 bugs in 19 mature controllers. These bugs have severe consequences. But it's really hard to guarantee controller correctness using testing, not just because the testing space is huge, but also because there's no general correctness spec for controllers. So we often need to come up with ad hoc testing oracles for catch the bugs we trigger. Also, controller bugs are often liveness violations, and liveness violations are notoriously hard to detect in a reliable way using testing or even model checking. So we start to rethink about how to achieve controller correctness. And in this paper, our goal is to build provably correct production-grade cluster management controllers using formal verification. And towards this goal, we make the following contributions. First, we present eventually stable reconciliation, or ESR, a formal spec for controller correctness. ESR captures controller correctness as a liveness property, and is generally applicable to different types of controllers. And to help developers verify their controller implementations that satisfy ESR, we present Anvil, a framework for building formally verified controller implementations. Anvil focuses on verifying liveness properties, but can also be used to verify safety properties. With Anvil, we have built 3 representative Kubernetes controllers and verified that they satisfy ESR. And these controllers manage critical cloud applications, which are ZooKeeper, RabbitMQ, and Fluentbit running on Kubernetes. These controllers achieve feature parity and the same performance compared to existing unverified mature controllers. At a high-level overview, to use Anvil, developers write their controller implementation in Rust, and then specify the correctness guarantee of this controller in a formal language, and then write a proof to show that this controller correctly implements the spec. The proof is checked by the virus verifier, a state-of-the-art verification tool for Rust programs. The controller implementation is directly compiled by the Rust compiler, and it can be readily deployed on any Kubernetes clusters, and it can be directly usable. There are 2 key challenges here: how to write the spec for controller's correctness, and how to write the proof. So for the rest of the talk, I'm going to focus on how we address these 2 challenges, and let me start with how to write the spec. The problem here is there's no existing correctness spec that is generally applicable for all controllers. Controllers are relatively new type of software, so we don't have standards such as IFC or POSIX to define their behavior. Also, for diverse controllers, their correctness is not uniformly defined by protocols such as Raft or Paxos. So to come up with the right spec, let's first look into how controllers work. The key here is a state reconciliation principle that all controllers follow. And let me explain it in detail. In cluster managers such as Kubernetes, the cluster state, including servers, containers, volumes, networks, and so on, they are all managed through some desired state, which is a high-level declarative manifest that describes what the desired state looks like. And the goal of the controller is to reconcile the cluster state to match the desired state. And this is done by continuously monitoring both the cluster state and the desired state and continuously updating the cluster state. So let me be more concrete. Let's say a desired state for a distributed application running on Kubernetes may specify that there should be 3 replicas and each one has a 10 gigabytes volume. And then the controller is supposed to bring up 3 replicas running in container, each has a 10 gigabyte volume attached to it. The desired state may change due to different deployment demands, for example, to scale up the application, and then the controller should react accordingly to bring up more replicas and allocate more volumes. So one potential way to specify controller correctness is to write a safety property saying that state reconciliation never goes wrong. But the problem here is that controllers may go wrong in many different ways for different reasons, like a data race or unexpected crash. And for different controllers, because they manage different applications or resources, they could also have different manifestations of their wrong behavior. So it's really hard to specify all the wrong ways in one safety property. So instead of trying to figure out every possible wrong state reconciliation, our insight is to focus on what a correct state reconciliation does, and we found it's really about liveness. So in principle, a correct controller should reconcile the cluster state to eventually match the desired state, no matter what happened in between. And we call this progress. And once the cluster state matches the desired state, the controller should always keep it in that state, and we call it stability. So we capture progress and stability in one clean temporal formula called the eventually stable reconciliation, or ESR. ESR says that for any state description D, if the desired state is and always is D, or in other words, if the desired state is fixed to D, then eventually the cluster state matches D and always matches D from then. ESR captures both progress and stability, and importantly, here there's a premise, that is, the desired state has to be fixed to D starting from some point. We need this premise because if the desired state keeps changing from D1 to D2 to DK and keeps changing, and then the controller will keep chasing a moving target, and there's no way for the controller to guarantee any progress towards any version of the desired state. Proving ESR gives you the guarantee that no matter how many changes the desired goes through, from D1 to D2 or to DK, as long as the desired state eventually gets stable, and then the controller will eventually make the cluster state match it, which is DK here. ESR is simple, general, and powerful. It's very easy for developers to write and inspect the ESR formula because all you need to know is the expected output from the controller, that is to match the cluster state with the desired state. And ESR precludes a broad range of bugs, literally any type of bug that hinders progress or stability. ESR focuses on the high-level state reconciliation principle, and it does not talk about any specific control implementation details. So now that we have the ESR spec, the next challenge is how to prove that a controller implements ESR. This proof is not easy to write for mainly 2 reasons. First, controllers run in complex environments. So to prove a controller satisfies ESR, we need to reason about not just the controller itself, but also its interaction with the environment. And second, ESR is a liveness property, and liveness reasoning itself is notoriously hard, because proving liveness often requires subtle liveness assumptions on the environment, and also complex temporal reasoning to prove certain things happen in the future moment or not. So Anvil addresses these challenges and reduces developers' proof burden with a set of features. So first, to help the developers reason about the controller's interaction with the environment, Anvil provides an environment model that describes the behavior of the system components that the target controller interacts with. And to help on reasoning about liveness, Anvil first provides a temporal embedding, which describes the important concepts in temporal logic, which is used to reason about whether certain things could happen in future or not. And on top of the temporal embedding, Anvil provides a set of reusable lemmas that can be directly assembled into developers' ESR proof. And we also provide a set of assumptions that are necessary for proving ESR. And finally, Anvil comes with a proof strategy that help developers to structure their ESR proof. And let me dive into the environment model, the Liveness assumptions, and the proof strategy here. Anvil's environment model basically describes the important system components that the target controller needs to interact with to help developers reason about the interaction. This includes an API server, a set of API servers that expose the cluster state to the target controller and interact with the target controller for reading or updating the cluster state. A client that may update the desired state to any from and any point. A set of built-in controllers that shares the same cluster state with the target controller. And an asynchronous network that connects all those components together. This environment model is basically a state machine, and it naturally captures asynchrony and concurrency challenges for controllers. And one particular example here is that time of check to time of use issues are allowed in this model, and the controller should be able to tolerate that. So let's be concrete. The controller typically often first read the desired state, and then reconcile the cluster state according to the read result. So here it read D1 and try to reconcile according to D1. But if the client updates the desired state in between the read and reconcile, let's say from D1 to D2, and then the controller will end up reconciling the cluster state for an old version of the desired state, which is D1 here. And this should not affect the controller's ability to eventually catch up with the new desired state and reconcile the cluster state to match the new desired state. And besides, this environment model also captures common failures that controllers should tolerate. In this model, controllers may crash for arbitrary times at any point and may stay offline for arbitrarily long time before it comes back. And the request sent by the controller to read or update the cluster state may also fail at any point due to, for example, network timeout. And the controller should tolerate all of those. So Anvil also provides a set of assumptions for proving Liveness. And those assumptions are important, are necessary, because Liveness is impossible in some adversary cases. One example here is that, say the controller is waiting to receive some network message before taking the next state reconciliation step, but the network somehow just never delivers that message to the controller. And even if the message is already in the network and ready to be delivered. And in that case, there's no way for the controller to make any progress. And we eliminate such adversarial case using the weak fairness assumption from TLA, which in this context means that if the message remains ready to be delivered, then it is eventually delivered to the controller. And another adversarial case is that the controller keeps crashing right after restart, and then it also has no way to make a progress. And here we use another assumption saying that a crash can happen arbitrarily times, but eventually it stops happening. And note that this assumption does not pose any limit on the actual number of crashes that may happen. So in this model, the controller can literally crash for hundreds or thousands of times, but it should still be able to get back to the state reconciliation path after the crash. So with the model and assumptions, we are ready to prove ESR, and Anvil provides a general proof strategy for developers to structure their ESR proof. This proof strategy basically decomposes the ESR proof into two major lemmas. The first lemma says that the environment is eventually stable. Here, stable means that the controller no longer crashes, and the desired state is fixed, and so on in this environment. This lemma is relatively easier to prove because it's mostly based on the assumptions I just mentioned, and it doesn't require complex reasoning on the control implementation itself. And the second lemma here says that starting from any cluster state, the desired state is eventually realized in this stable environment. And the key here is that in this stable environment, the controller can steadily make a progress towards the desired state without getting interrupted by crash. So it's easier for developers to reason about the progress in this stable environment. But also note that this ending cluster state results from ending possible interleaving of controller actions and failures, which means that we still need to reason about all kinds of corner cases of state reconciliation. And this is exactly how we can discover deep controller bugs using formal verification. So with Anvil, we have built and verified 3 Kubernetes controllers for managing ZooKeeper, RabbitMQ, and FluentBit on top of Kubernetes. And for each controller, we use the existing, mature, and widely used controller implementation as a reference to write our own implementation. And our controllers provide feature parity. They implement important features, including scaling, upgrading, reconfiguration, and so on. The verification effort is manageable. The proof-to-code ratio is around 4.5 to 7.4. And notably, it took us around 2% months to write the proof for the first controller. And with the experience from the first controller, it only takes us around 2% weeks to write the proof for the other 2 controllers. And the verification helped us to discover 4 deep bugs in our controllers, and 2 of them actually also exist in the reference controllers. And for evaluation, we evaluate the end-to-end performance and the correctness of the verified controllers. The verified controllers achieve the same end-to-end performance as the reference controllers. And for testing, we use our previous testing tool, Acto and Sieve. We generated in total over 1,800 end-to-end functional tests and crash tests for the 3 verified controllers. And we found in total 1 bug in the trusted spec of the ZooKeeper API written by us for verifying the ZooKeeper controller. I know that no bugs are found in the verified code. To conclude, controller correctness is a pressing and challenging problem. And our goal is to build probably correct and production-grade cluster managers such as Kubernetes using formal verifications. In this work, we present ESR, a formal spec for controller correctness, Anvil, a framework to help developers verify their control implementation satisfy ESR, and we have used Anvil to build 3 verified controllers, and we are currently building and verifying more controllers. All the code is open source on GitHub. And finally, I will be on the job market in the upcoming cycle looking for research positions in both academia and industry. Thank you. I'm ready to take questions.